Hey, we're going back with the textbook, and so here we're going to be jumping into taking a look at actually two sections, section 1.3 and 1.4. They're very, very simple. So the first one is all about slope fields, and so basically the idea is that we're going to be taking a look at sort of a qualitative approach to differential equations, and in this case we're looking at sort of a whole bunch of hashes that we're going to be making. So basically you take your differential equation, dy dx is equal to f of xy, and for each x and y it tells you what dy dx is, which is a slope. And so what you do when you're making a slope field is you just go through and you make a whole bunch of hash marks, all in the plane, or at least in a region you care about, usually around some sort of initial value. And then from there, you drop your point in there and you assume it goes to the right, and then you just follow whatever the slope tells you to do. And in the textbook they also go to the left as well, and or at least maybe right and left, depending, I guess, for you, your perspective, if I look in that direction. But yeah, so that's what slope fields are going to be. So there's going to be a couple things we're going to be doing. First, we're going to have to make slope fields, and that's really kind of a tedious process. You just go through and do a whole bunch of little tick marks, doing a whole bunch of like back envelope calculations, and then you just put them up on a field, and then you draw things. And then there's a couple of things that you can do that make life a little bit easier. And so what you do is you look at sort of the level sets of fxy, which are basically all the points that sort of agree. So you're looking at all the f of xy that are, say, 0, for instance, and that'll give you a curve. And then on that curve, you're going to have a whole bunch of horizontal tick marks, because 0 slope means that you're just horizontal. And so, and then you look at, say, f of xy is equal to 1, and that tells you your slope is equal to 1 at all those points. And so that's going to give you a new curve where all the slopes on that curve are slope 1, and then you do slope 2, slope 3, etc., until you have a whole collection of curves with each one of those curves having a different slope on them, not the slope not matching the curve. The slope is independent of the curve, and so don't confuse that. I had a lot of students just basically drawing tangents on these curves, and that is not the answer. What it is you say that I want my slope of 1, then f of xy gives me this, and then it gives you a curve like a polynomial or an ellipse, or it's a circle or something like that. And then on that circle, you have slopes of 1, which are 45 degrees all the way around it, right? And that's the sort of thing we're going to look at. I'll get into more detail in there later. Okay, and so those are going to be the two ideas we're going to have. We're going to have slope fields, and we're going to have what are called isolines, which are those curves that correspond to a single slope. Then after that, I want to jump into section 1.4. And so where 1.3 gives you sort of a qualitative approach to differential equations, section 1.4 gives you a quantitative approach. And so before we had a computer algorithm that went through Picard's iteration, and that gave us a solution. And so this is something that's a little bit different. So Picard iteration really only works if you have polynomials, because you have to be able to, say, integrate polynomials. And so what you can do instead here is you can actually turn it into integrating time steps. And actually no real integrals that you're ever going to really deal with by hand. It's basically going to be what is called Eulers Method. So Euler has a really simple method where basically you start at a point and you say, what is my slope at this point? And so you plug in your values at your current position of both your time and your position, so t or y or x and y, whatever your independent and dependent variables are, and then you get a slope, and then the algorithm says, okay, well, pretend this is a straight line with that slope, and you follow it that far. But if you're just going a straight line, that isn't truly representing the curve. So for instance, if we have dy dx is equal to y, then it's an exponential, and so a straight line definitely is not going to match an exponential. But at the very least, it shouldn't match it locally, because all differentiable functions have a tangent line, and so they are approximately linear at all their points. So what you can do then is you can keep that step size very, very small, where you assume that it's going to be linear. You just make it, we call it step size h. And as h goes to be very, very, very small, you shouldn't be deviating very far from your actual solution. And so then basically what Euler's method does is it gives you a method for getting a sort of a rough quantitative approximation of your differential equation. And in fact, it gives you such an approximation that you know that if h goes to 0, then theoretically you should be able to get almost perfect approximation of your curve. Now, that actually doesn't end up holding up quite as much as you'd hope, and the reason why there is really just comes down to rounding errors and things like that. But you know, theoretically, at least for the differential equations class at the 2000 level, we'll assume that it gives you going to h, taking it to 0 is going to give you perfect approximation. Okay. Anyway, we're going to jump into that, and yeah.
What we're looking at is section 1.3 first, and then we'll get into section 1.4. And so the book calls this direction fields. What I learned was it was called slope fields, same thing. So if I end up using direction field versus slope field in here, you know, just be assured they're the same thing. So the general idea is that you're going to be given a differential equation. And so let's go ahead and start off with something like this. dy dx is equal to x squared minus y. Okay, and I'm going to show you how to make a direction field out of this. So a direction field is basically a whole collection of little tick marks that you make in the plane. And so I can pick a few points, so say 1, 2, 3, -1, -2, -3. We can have another 3 here, so we have, say, 2, 3, 1. And down here, we can have, say, -1, -2, -3, right? Okay, and so the idea is that we're going to pick each one of these points, and we're going to put some sort of slope in there. So it could be flat, it could be really steep, you know, etc. Just one slope per there, and so let's go ahead and take a look. So I'll put the points in green. So here, we're going to have that. And so I'm looking at the point, say, 1, 1. So at x equals 1, comma, y equals 1, what do we get? Well, we get dy dx is then going to be at 1 squared minus 1. And so that is actually 0. So what we have here now, let's do this in red, is we have a flat slope. Okay, so that's our first little point. Now let's pick another point. Let's pick here. So now we are looking at the point x equals 1, y equals 2, right? And this is going to get tedious quick, but yeah, let's see. So we're going to have 1 squared minus 2, and it's going to be -1. So in red, we can have a slope that's a -1 slope, right? Let's see, let's do some on the axis. And so let's just take a look at this point and this point and this point. And let's take a look at that point here. So let's do them real quick. We have x is equal to 0, and let's take a look at the point y equals 0, for instance. Then we'll take a look at x equals 0, y equals 1, x equals 0, y equals 2. And these, and let's go ahead and work those out. So in each of these cases, we're just plugging in. It's really, really simple. So we're making a slope here, and so for the point x equals 0, y equals 0, I end up getting 0 minus 0. So again, that's 0, right? And then for the point x equals 0, y equals 1, I get, say, dy dx is equal to 0 minus 1. And that's going to be -1 again. And then here we have dy dx corresponding to this guy. And that's going to be, let's make sure it's lined up. So it's going to be 0 minus 2. So a -2. All right, so let's go ahead and put these slopes in. So for the point where we had 0, 0, again, we had a 0 slope. And for the point 0, 1, what did we get? We had a -1. So we had that there. And for the point 0, 2, we had -2, so it was really steep. So it was something like that, right? Now, as far as your accuracy on an exam, I am not going to be too picky. Just as long as it's, say, if it's supposed to be negative, make sure it's negative. And if it's supposed to have a -2 versus a -1, make sure the -2 looks steeper. And if it's 0, just make sure it's flat. Right. Now let's take a look at this point here. And so what are we going to get? Well, we have the point x equals 1, y equals 0. And so we're going to have dy dx is equal to 1 squared minus 0 is equal to 1. And so we can go ahead and put a tick mark here like that. Okay, so that's a good little cloud of things going on here. Let's just go ahead and do a whole bunch more points. Again, we can have the point, say, say x, stay consistent. So let's take a look at x equals 2 and y equals 0, x equals 2 and y equals 1, x equals 2 and y equals 2, etc. And after that, we'll stop there. So here we have dy dx is equal to 2 squared minus 0, so that's 4. We have dy dx equals 2 squared minus 1, and that's going to be 3. And we have dy dx equals 2 squared minus 2, and that's going to be 2, right? And so that's corresponding to these points here and here. And let's see. So let's go and put the marker on them. All right, so at the point x equals 2, y equals 0, we had a 4 slope. That is really, really steep. And if this doesn't look steeper than 2, then I mean that I can't do much about that. And then if we move up 1, the 3 is supposed to be slightly less steeper, and the 2 is going to be slightly less steeper than that. I don't know. So that's what we get. Let's see. So what does this end up looking like? So basically, the idea is that if we want to solve an initial value problem, right? And so if we have an initial value problem, so suppose we have y of 0 is equal to, say, 2, then that means that our initial point is going to be here, right? And the idea is that we're just going to follow these slopes down and back up, right? So we're thinking our solution should look something like that based on our slope field. Now, I'm going to go ahead and plop right here the actual slope field that you can compute, say, with MATLAB. And so, hey, we're going to have another midnight with MATLAB tonight. But I'll put that there later for your reference. And yeah, so you can see what the slope field actually looks like when at higher resolution. All right, so now let's go and take a look at another example. So you should get the idea by now. So the idea is that we just have a differential equation. We're trying to figure out what are some slopes, and we're trying to do this by hand as much as we can. And so, so here's another example. We have dy dx is equal to, say, minus x over y, right? And here, let me tell you a secret. This, again, can be solved with separation of variables, which we will get to next lecture, actually. And so we can actually write this as, say, y dy is equal to minus x dx. Integrate both sides, and we get y squared over 2 is equal to minus x squared over 2 plus some constant. And so then what you see then is you have x squared over 2 plus y squared over 2 is equal to a constant. And what is that? Well, that is a circle, right? So, so as we make the slope field, we should be keeping an eye out for something that's kind of circle-y. So let's go ahead and do that. All right, so here we go. All right, so let's again mark out a few points. Right, and so we'll call this 1, -1, say -1, 1, -1, and we have 2, -2, -2, and 2. All right, now let's go ahead and figure out these points. So pretty easy. Let's go ahead and take a look at all the ones that we can. Turns out that this is actually sort of symmetric, right? So we're only going to have to figure out one quadrant, and then I can use some symmetries to populate the rest. Basically, because if I swap x with negative x, all it's going to do is we're going to have a minus sign. It's going to flip it. So basically, all the slopes are going to be opposite whatever they're supposed to be when you go from, say, this quadrant to this quadrant, and then this quadrant to this quadrant. And so we just need to figure out like one quadrant here, and then the rest we can copy around. All right, so there's one problem right away, and we can't do this point. In fact, we can't do any of these points. And why can't we do these points? Well, it's because we have a y in the denominator. So we're going to have to sort of infer what's going to be going on in those areas. It turns out this y in the denominator is going to be kicking out what are technically vertical slopes. So I can actually go ahead and put those in, but strictly speaking, this is undefined. But at least in this case, it's sort of a limiting process. But this one, at the origin, there's nothing we can do because we have 0 over 0, and that's really not something we can handle. Okay, so all right. So then, what happens at the other points? And so, at let's see, let's keep my colors consistent. So at y is equal to 0, we have vertical asymptotes. Right. Now let's take a look at, say, x equals 0. Well, then this is going to give us dy over dx is equal to minus 0 over y. And so this is going to be 0 no matter what y is, with the exception of y being 0. And so that tells us that we're going to have flat slopes all through here. Okay? All right. Now let's take a look at what happens when we have a more specific point. Let's take a look at x equals 1 and y equals 1. What happens? Well, then we're going to have dy dx is equal to negative 1 over 1. So that's just negative 1. So that's something we can do pretty easily. It's going to be a slope there. Now, what I just told you is that if I flip the sign of either y or x, it just sort of flips the slope. So we're going to have a slope here like that, a slope here like that, and we're going to have a slope here like that. And so, so there you go. Now, let's take a look at what happens at, say, the point 1, 2. So we have x equals 1 and y is equal to 2. What happens? Well, we're going to have dy over dx is equal to minus 1/2. So it is a negative slope, but it's not quite as steep. So something like that. And then, again, we can use symmetry, and we can see sort of just mirroring what we have here. It gets that. Okay, now let's see. We only really have 2 points left to figure out, and that's easy enough. So we're going to have, say, x equals 2 and y is equal to 1. What do we get? We get dy over dx is equal to negative 2 over 1 is equal to negative 2. Okay, so that means it's going to be steeper than the 1, and so it's going to be up like that. And then we're going to have this guy's up like that. Oh, we missed a point. That's what happened. Should have a blip there. Okay, and now we're going to have that. Okay, good. And again, mirroring and mirroring there and there. And finally, let's take a look at the point x equals 2 and y equals 2. By this point, you get the idea. So we have dy over dx is equal to negative 2 over 2. And so it's going to be negative 1. And so slope here, slope here, slope here, slope here. Okay, so that does look kind of like a circle. And so the idea is that, suppose we have y of, say, 0 is equal to 2. And what's going to happen? Well, we're basically going to start at 2, and we're just going to go around like this. But can't quite do that because this is supposed to be a function. So we go like this, and we're just going to stop when we get here because a function actually isn't defined if we start going backwards. So We see intuitively that it is making a circle, but since it needs to be a function at the end of the day, we're going to stop here. We could think of this as a path and a vector field, but that's more Calc 3 than it is differential equations. You could also include sort of going backwards, so something like that, if you'd like. And yeah, and that's the that's the slope field. Okay. So let's take a look at another one. And so this is called the logistic equation. So so here, this is the logistic equation. And it is given as this, so it's dp over dt is equal to p times 2 minus p. Now what's interesting here is that we actually have no time dependence. And so this is fairly nice because it'll make things a lot easier. So let's go ahead and take a few interesting looking spots and see what we can do. So the logistic equation is for modeling population. So so this is P is the, oh man, where'd my handwriting go? So I'll say that P is the population at time t of a certain species. And it obeys this differential equation. And it obeys the differential equation star. And so we'll call this star. And so so they're asking a few things. So they're asking, for one, they want us to make a direction field. So let's go ahead and make a direction field. And there's a few tricks to this. So we're going to say it's 1/2, and I'll say this is at 1, and this is at 1.5, and this is at 2, and let's say it's at 2.5, etc. And we'll say it's at -1/2. Okay, so what we can do is we can go ahead and make a whole bunch of tick marks. I'm going to make them all along the y-axis, and there's a reason why I'm going to make them over the y-axis. So let's go ahead and work them out. So let's go ahead and say y is equal to, say, 0. What happens? Well, we have dp dt is equal to 0. Well, I shouldn't say y anymore because p is playing the role of our dependent variable. So I'll just say p is equal to 0. So that gives us dp dt is equal to 0 times 2 minus 0, which is just 0. And so that means that our slope here at 0 is horizontal. Okay, now let's go pick another value. Say p is equal to 1/2. Well, then dp dt is equal to 1/2 times 2 minus 1/2. All right, well, what does that give me? Well, it gives me 1/2 times 3/2, and that gives me 3/4. Right, so it's not quite 1, but it's, oops, let's try to do it in red. And so it gives us this. Okay, now let's take a look at, say, p is equal to 1. What is dp dt? Well, it's going to be 1 times 2 minus 1, and that's going to be 1. Okay, so it gives me a slope of 1. Should be a good 45 degrees there. And now let's take a look at p equals 1.5. So that's dp dt is equal to, say, 3/2 times 2 minus 3/2. And it's going to be, say, 3/2 times 1/2 is equal to 3/4. Okay, so we're going back to the 3/4 mark. So something like that. All right, finally, let's take a look at, say, p equals 2, and then p equals 2.5. And then we got dp dt is equal to It looks like 2 times 2 minus 2 is just 0. So again, we have a slope of 0. And finally, at 2.5, we have dp dt is equal to 2.5 times 2 minus 2.5. So that's equal to, say, 5 halves times 1/2. And it's going to give me 5 quarters. So a little bit bigger than 1. Right. Sorry, minus signs should be in here. So it was 2 minus 2.5 should give me negative half. And so that should give me a negative 5/4. So it's going down a little bit steeper than 1. So something like that. Okay, so why did I care about only these values? And let's not bother with negative 1/2 at this point. Well, it turns out since this doesn't vary with time, as I keep progressing forward and forward, it's going to give me exactly the same values. So I can just go ahead and copy that column all the way through. And so let's go ahead and do that. So here, 0 slope all the way through. Here we have a slope of 3/4. Here we have a slope of 1. And here we have a slope of 3/4 again. Here, slope of 0. And here we have a slope of minus 5/4. Okay, so let's just think about what happens when we do some things here. So if I were to put a point here, it stays 0 whole time. Makes sense. If you have nothing in your population, you will sustain having nothing for your population. If I have something here and I move forward, so if I have say 2, and I think is measured in thousands, then we stay at nothing. And if I start here, we see that we're going to come up over this way, and it's going to become asymptotic to this. Okay, and if I start above, it's going to decay. All right, so what does this say about the population? Well, it looks like this is sort of the stable equilibrium population that we're going to get. And if we start below, we end up going up to it. And if we start above, we go down to it. Note that we can't go from the top and cross down, because that means that we wouldn't have a slope of 0 here. So so basically this becomes a limiting line here. Okay, so now let's take a look at what they're asking in the section. So population, say I think it's in thousands. So the first thing is that they say they're asking if the initial population is 3,000, then what is the population as t goes to infinity? So basically we're saying that p here is equal to 3. Well, I can, if we did one more of these guys, we can figure out exactly what it should be. So if I put here at 3, then we see that we're going to have, again, a negative slope. It's going to be 3 times 2 minus 3, so it's going to be negative 3. So it's going to be really, really steep. Let's put something like that. And so, all right, so now we can make a judgment of what happens. And essentially, if we start here and we play, we're basically going to decay down to 2,000. So, so basically, let's go ahead and write this in pink, I guess. So the solution is the population will tend to 2,000 as t goes to infinity. Okay. Right, now let's take a look at the second question. Can a population of 1,000 ever decline to 500? So can a population that starts at 1,000 decline to 500? All right, that's the question. So let's take a look. So if we're starting at 1,000, that means we're starting here. Well, the slope tells us we need to be going up, and we need to be going up until we hit 2,000. And so the answer is no, it cannot. No, the population will increase to 2,000 to approach 2,000. Okay, so let's take a look at the third question they have in the book. Can the population of 1,000 ever increase to 3,000? Can a population of 1,000 increase to 3,000? Let's take a look. So again, we're starting at 1,000, and we should be tending to 2,000. And what would happen if somehow we got up to, say, 3,000? Well, then that means that at some point we had a positive slope going through the 2. And so that can't happen, because the slope at 2 is always 0. And so, so the answer is no. No, because if we did, then the slope at, say, p equals 2 would be non-zero. Right. So that means we can't cross here, right? Okay. So cool. And so let's talk about a little bit about what happened here. So this was a nice little population model, and what we saw was that all we needed was the information that we had here, and then we could copy it here and here and here. And so there's a name for this sort of equation, and so this is what is called an autonomous or time invariant differential equation. Okay. And so whenever you have one of those, you can just only worry about what happens here and then draw the rest. All right, so now let's talk about isoclines. So what you saw is when we went through and we did these 3 examples, here I got it was too tedious to keep going, so I just stopped. Here we had a slope, and we exploited all sorts of symmetries in order to only use these values to copy them everywhere else. Then here we used the fact that it was autonomous to just basically make a column and then just copy it over. And so we can't always take advantage of all those ideas, but there is something you can do, and I think it's fairly interesting. So for instance, so this is going to be called the method of isoclines. All right, and the method of isoclines is basically a shortcut to get a whole lot of values all at once, and so let's go ahead and talk about it. So basically, the idea is that we're going to be setting. So basically, an isocline is a collection of points where a given differential equation has the same slope. So these are usually a collection of points. I can generally say is a curve, usually. So Let's take a look at an example real quick, and then we'll talk about how we can actually exploit this idea. So let's take a look at, say, I don't like the examples they have in the book because they're all like straight lines. So let's take a look. Dy dx is equal to, well, we had that nice one, x squared minus y earlier. And so let's go ahead and take a look at the method of isolines used here. So this is one I gave up on because it was too tedious. So let's see if we can make it less tedious. And so what I'm going to do is I'm going to ask questions. I'm going to say, when is dy dx equal to, say, -1? When is equal to 0? When is equal to +1? When is equal to 2? Right? Let's see if we can answer these questions. So, if dy dx is equal to, say, -1, so all my slopes are going to be sort of 45 degrees there. Well, I know my differential equation should be equal to x squared minus y. So I take this, and that's an equation. It tells me that indeed I'm going to have y is equal to x squared minus 1. All right, now let's take a look at another one. So I'm going to have dy over dx. When is that going to be equal to -2? Well, that's going to be still x squared minus y. And in this case, it gives me another equation, another curve. Y is equal to x squared minus 2. Or, sorry, that should have been +1, and this should be +2. If only I could do my algebra. All right, so now let's take a look. Dy dx is equal to, say, 0. And so it's going to give me x squared minus y. And so then that tells me that y is equal to x squared. Oh, keep my colors consistent. So it tells me that y is equal to, say, x squared. And say dy dx is equal to 1. It's going to tell me x squared minus y. It should be, change color, y is equal to x squared minus 1. And finally, last one, dy dx is equal to 2. It's going to still be same differential equation. This is my slope. And so now I am going to go ahead and see that this is going to give me y is equal to x squared minus 2. Okay, so now we have a whole lot of isoclines. And so here in purple are the isoclines. And let's go ahead and draw them. So let's go ahead and start with the easiest one, this one, y equals x squared. And so it's going to be something like this. Yeah, no mystery. It is a parabola, right? Now, that was the isocline corresponding to this. This is my slope. And so we have a curve, and separately we have a slope. And so now that I've drawn my curve, now I can draw my slopes on it. So don't confuse them, but basically all along here, we should have a slope of 0, which means it should be horizontal. Okay, so it's nice. And so you see instantly we have like an infinity of like points in our slope field. And so that's really nice. That's a whole lot of points I didn't really have to evaluate otherwise. We just used a little bit of pre-calculus and we got there. All right, so now let's draw another isocline. And so let's go with, say, -1. And so the one at -1 is, shifted up, same guy, just, so I'm left-handed, so this actually becomes difficult for some reason. Okay, so there we go. So these are all my, so this, we'll say it was at 0, and this one is at 1. And so all of these guys have a slope of -1, right? So that means they should be going down at like 45 degrees. It's tempting to be influenced by the curve. Try to put that out of your mind as you draw these. And I might not have been completely successful, but all of these should have the same slope. Okay, now let's go to the next one. So we have this guy here. And so this is starting out at 2. And again, we have this parabola. So it's x squared plus 2, right? So is x squared shifted up twice. Right? And what do we get? Well, So all the slopes here are -2, and so this should be steeper than the one below it. And that's all I care about when it comes to an exam, is that you make this more steep. Really, this is a qualitative sort of thing. It doesn't have to be super precise. We're just trying to get an idea of what's going on here, using as little calculus as possible. We're pretending that we are calculus boneheads and we don't know how to do anything with calculus, but we can do arithmetic and we know what a slope is, and that's all we're using here. So now let's keep going, and we have 2 more curves that we're going to do, and what is this going to give us? So here we're going to start off with, we have this slope of 1 and this isocline corresponding to it, and so again it's just x squared just shifted by 1, right? There we go. And so now all of these guys had a positive slope of 1, so up at 45 degrees. Again, do not get influenced by your curve. It's really, really hard to do. But yeah. And finally, last curve is this one, corresponds to a slope of 2. Try not to get too tedious here. And so, let's see. And so this should be even steeper. It's getting really tedious. Okay, good. Now let's talk about it. So we have our slope field. Now that we have a slope field, let's talk about what happens when we have an initial point, say y of 0 is equal to, say, -1, or even, so it's not always at 0. Let's say we have -1 at -1, right? So we're going to be something like over here, right? So what's happening? Well, this guy says we should be going up, and we should go flat when we get here, and then up, kind of. It looks like something like that, and it should just kind of go up. This is kind of confusing. And if we start over here, it's maybe a little bit clearer. We get down to this, and then we start going up again. And if we go over here, we're going to go down, and start going up again over here. And so basically things are generally looking like they're going up in this direction. They'll start high, flatten out, and then go back up. And that's sort of the qualitative idea of what the solutions here are doing in this curve. Okay, so that's the method of isoclines. You basically make up curves, and once you make up a curve, it could be a parabola, it could be an ellipse, it could be a circle, and yeah. In any case, later on I can send you a video that goes over more problems out of the section. And yeah, so that's the method of isoclines. Okay, so now we've seen how to do the method of isoclines and also slope fields in general to get sort of qualitative view of what our differential equation is going to do. So the whole idea here is that, you know, we just have a bunch of tick marks that we sort of drew ourselves, and then we kind of try to put plots to them to the best of our ability. Now, what we'd like though is we'd like something that's a little bit more objective. So this involves a little bit of guesswork. You know, it involves sort of a human element. How can we take the human element out of it and get something that's sort of numerically accurate? So this is what we use Eulers Method for. And so this is jumping into section 1.4, but really it's only a couple of examples. So 1.4 basically is it's called the Approximation Method. Of Euler, right? It's not Euler, it is Euler. So basically the idea is that we have an initial value problem, so IVP, and so this is going to be, say, y prime is equal to f of xy with y of x naught is equal to y naught, right? And our goal is to be able to come up with some sort of way of doing this numerically. Well, basically, this is the next boneheaded approach to the problem, and it turns out, again, boneheaded approaches work. So the idea is that we start here. Let's choose a different color. Let's go to purple. All right, so we started here and we're at x0, y0. And we know that this is where our system starts. So it's the one point that we know for sure is definitely going to be on our curve. So what do I do next? Well, what I can do is I can ask, what is the slope here? And so just like what we had before, we can go ahead and plug it in. Why don't we actually do like a solid example, and we'll go with, say, y prime is equal to, say, 1 plus x squared. Actually, let's just say 1 plus x. And we're going to assume that y of, say, 1 is equal to 1, right? So that looks roughly right. Let's say y equals 1 equals 2. That seems to match the graph a little bit better. Okay, so what is the slope going to be? So if this is the point that's actually, say, 1 comma 2, like what we're saying with this initial value, well, we can go ahead and compute what slope should be. So slope should be, so y prime, oh, and let's make this maybe a little more string. Let's involve y. All right, there we go. So, so what we're going to get is we get 1 plus, say, 1 times 2 is going to be the slope there. And so this is going to give me a slope of 3. So we know that slope is going to be fairly steep, something like that. Okay. So then what I could do is I could say, okay, well, this is my differential equation. It goes in this direction. And so the idea there is that if I pick a point here on this curve, roughly if I don't go too far, I should match what the solution should be. And so how do we quantify that? Well, what I'm going to do is I'm going to demand that our step size stays small. So we don't go very far. We'll just go some h, where h is a small quantity. And then basically we're going to pick this point here, right? And so that's that point. Then what we do is after we get to that point, we kind of guess the next one. Well, we don't have to use like the graph in order to figure this out. We can actually compute this directly. And so what I'm going to do is I'm going to start at my initial point. And so I'm going to start at, say, y0. Then I'm going to add h times f of x0, y0, right? And so this is going to be my slope. And we follow that same slope, h step size. So we call this our step size. And then we started here. We started at y0. So I'm going to get a new point. We're going to call this y1 after I do this computation. So let's pick h to be, we're going to let h be equal to 0.1. This is sort of a typical value we're going to use. And now let's see what happens. So basically y1 then is going to be where we started. And so we started at 2, that's this guy, say y0, and this is at x0. And we're going to move forward in x by h, and so this is going to be 0.1 times what we have over here now is going to be 1 plus x times y. Now we're going to use x0 and y0, and so then this is going to be, say, 1 times 2. Okay, so this is going to give us then 2 plus 0.1 times 3, and it's going to be 2.3, right? So instead of being at 2, it looks like my figure was a little bit too dramatic, and so we went from 2 to 2.3, which was roughly there. And so there. And this is a step size of h, and h in this case was just 0.1. So remember though that this was x equals 1. So we say that y1 approximates y of x plus 0.1, or 1.1. So basically we're saying that this is roughly y1, which is equal to 2.3. Okay. Now the idea is that if I keep shrinking h, then this approximation should get better and better. And there's a way to quantify that, but in this class we won't talk about that too much. It turns out Euler's method is one of the slower methods of doing this sort of thing, but it's also the easiest to understand. So that's what we got there. Now, if we want to figure out the next one, well, we can do the same process. We can say, well, I want to know what y2 should be. What is the next approximation? Well, that's going to be y1 plus h times f of where we are now, which is x1 comma y1. And now, if I just plug everything in, then I see that y2 then it should be equal to, say, 2.3 plus 0.1 times f of 1.1 comma 2.3, right? And so then we get y2 is going to be 2.3 plus 0.1 times 1 plus 1.1 times 2.3. And we can calculate that and figure out what that should be. I don't really feel like doing that right now. Should I do that? I should probably do that, right? I don't want to do it. Okay, well, let's do it. So the only tricky bit is going to be this one. It's, so it's going to be, say, let's do our side 2.3 times 1.1. And what's that going to give me? That's going to give me 3, 2, 0, 3, 2, and 3, 5, 2. And so, boop, there we go, 2.53. And then we're going to add 1, so we're going to have 2.3 plus 0.1. We have 2.53 plus 1, so it's 3.53. And so this is going to give me 2.653, right? And so that's going to give me my next point. So here is going to be the next point if we go from another 0.1 forward. And so we're going to be roughly around here. And so, boom. Anyway, so yeah, this doesn't really look great on a graph, especially when I chose such a small size. But I'll show you guys in MATLAB how that ends up looking. So yeah, so this is Euler's method. So let's jump into another example. And so let's take a look at, say, example 1 from the book. All right, so here they give us the initial value problem. Y prime is equal to x times the square root of y. And this is, the initial point here is y1 is equal to 4, so we know this is on our curve. And so they want us to use Euler's method with step size h equals 0.1 to approximate the solution to the initial value problem. And so they give us, I'll call it a star. At the points x equals 1.1, 1.2, 1.3, and 1.4. Okay, so we'll just do it really for like the first couple, and then we'll leave it at that. Just because it's going to get really annoying really quick to do the square root. But let's go ahead and do it. So let's go ahead and start plotting here. You don't have to plot, but it's really going to help you visualize this. So 1, 2, 3, 4. So up here 4. So this is where we start. Okay. So we have our initial value, and the idea is that we're going to have each successive bit is going to be like this. So we're going to have y of n plus 1 is equal to yn plus h times f of xn, yn, where xn, where we go from x0, is just equal to your initial value, x1 is equal to x0 plus h, x2 is equal to x 0 plus 2h, and etc. And we're given h, and y-ins we just make one at a time and build up through this, right? So we have y of 0, we have x of 0 in this case is equal to 1, we have y of 0 in this case is equal to 4. Okay, so let's go ahead and take a look and see what y1 should be. So y1 is going to be equal to y of 0 plus 0.1 times f of 1, comma 4. So in this case, we're placing here x of 0, and we're putting a y of 0 in here, and y of 0 here. And so, let me just go ahead and do that. It's going to give me 4 here, and there we go. Now I go and plug in f, and so it's going to give me 4 plus 0.1 times, we have x times the square root of 4, which is 2. And so it's going to give me 4.2. Okay, so we went forward by 0.1, and so we went to boop right here. So this is sort of at 1.1, and we're being told that now we're moving from 4 up to 4.2, right? So boop, like that. Okay, now let's see the next one. Let's take a look at y2. Well, y2 is going to be y1 plus h times f of x1, y1. And let's see, so that's going to be 4.2 plus 0.1 times f of 1.1 times the square root of 4.2. Okay, now this is me grabbing my handy dandy calculator, because I take the square root of 42. What would that be? Anything nice? Somewhere between 6 and 7, right? Because 6 is 30, 36. Nope. Not doing that in my head. Let's see. So I'm going to have 4.2, and I'm going to take the square root, and that is 2.049, let's say. So I'm just going to say this is going to be 4.2 plus 0.1 times 1.1 times 2.049. It obviously goes on beyond that, but I'm just going to stop there. All right, and let's multiply that times 1.1, and add it to, then multiply it by 0.1, and add it to 4.2. All right, so at the end of the day, I get 4.5149. I'm probably going too far with the decimals. I didn't include all of them here. But yeah, okay, so this is roughly what I get. And so this gets to about 4.5, so about here. This is at the point 1.2. Right, now if I wanted to go on and I want to calculate y3, and so this gives me y2, and y2 corresponds to x2. So this is going to be, we're going to ultimately get the point x2, y2, and this is going to be the point 1.2, comma 4.5-ish. So now we want to go on and find y3. Well, y3 is going to be this guy, so it's going to be 4.5149, so this is what we got from y2, plus h, which is 0.1, times f of 1.2 times, which is going to be x2, times square root of, say, 4.5149, etc. And this guy is the square root of y2. All right, so putting all these guys into our f. Okay, so you can work that out, and whatever you get is whatever you get. Now, what I would expect you to be able to do is get from, say, y of 0 to maybe this value. I'm not going to ask you to do square roots or anything crazy on the exam. I want you to be able to do this by hand because it is instructive to do that about 4 or 5 times. So if you see anything like crazy multiplication or square rooting or anything like that, just rest assured I'm not gonna ask you to do that. But you should be able to do some basic arithmetic. Okay, so but that's basically the idea. So let's formally state what we're talking about. So Euler's method basically can be broken down in this way. So for an initial value problem, where we have y prime is equal to f of xy with y of x naught is equal to y naught, we have a recursive algorithm. So first we select an h bigger than 0, typically small. And then basically for each yn, we can get yn plus 1 as yn plus h times f of xn yn. And then that's what we get. And yeah, it's not too bad. Okay, so let's see. Is there any other? Yeah, okay. So let's take a look at another example, and then we'll call it a day. So this is example 2, and basically what they're saying is that we're going to use Euler's method to find approximations of the solution to y prime is equal to y with y of 0 is equal to 1 at x equals 1 using what do they say? 1, 2, 4, 1, 2, and 4 steps. Okay, so first of all, let's go ahead and figure out what they're actually asking us to do. So they give us this guy, let's color it red, and they're asking us to figure out the solution at x equals 1, right? And, all right, T is part of me, just wants to make sure it stays square. Yeah. Okay, so basically we want to figure out the solution to this at x1. So let's go ahead and just see what sort of solution we get. So we know we're at an initial value problem of, say, y of 0 is equal to 1, and we know we have the problem y prime is equal to y. Well, at this point, I've shown you enough times that you should be able to figure this out. So we have dy dt is equal to y, and so then we have dy over y is equal to dt, and if we integrate, we get natural log of y is equal to t plus c. We'll assume y is positive, and then that tells us that y is equal to e to the c times e to the t, and if y of 0 is equal to 1, then that tells us that e to the c should just be 1. So we have e to the t. So it's the exponential function. We're trying to figure out what the value is here, and this is e to the 1. And so it should be about 2.717 or something like that, 2.71. Okay, so now let's see how close we get to that. So let's get a nice big graph. Shoop. And we'll start, and we'll call, like, say, 2 units, and we'll start here at 1, and we know we should get to about 2.7 should be roughly around here. Okay, so now they're telling us to use several step sizes. So this is going to determine h. So we're basically going to say one step size basically means we want to jump there with one h. So so for step size 1, we have h is equal to 1, And let's see what we get. So basically, we know x of 0 and y of 0. So x of 0 here is 0, and y of 0 is equal to 1. And so we get y1 is if we plug in y of 0 plus h times f of x of 0, y of 0, right? But we know what all those are. So we have 1 plus, say, h is 1 in this case, and times just y naught, right? Because f is just y. And so this is going to be times 1. So this gives me 2. Right? So where does that land me? Here. And so let's put this in, say, purple. So we get here. I'll put a purple triangle. So that's step size of 1. All right. Now let's do step size for 2. 2 steps. So 2 steps gives us step size of 1/2. So h is equal to 0.1, right? Because we're going to go basically here. And so we're going to go 1 step, 2 step, and that means that we stop in the middle at 0.5. Right? So let's go ahead and take a look. So what do I get? Let's do this in red. So I'm going to get y1 is equal to y of 0 plus h times f of x of 0, y of 0. But again, y of 0 is 1 plus step size now is 0.5, and then times 1, right? And so it's going to give me 1.5. So here, going to put a little red circle. That's where we end up. This is 1.5. Right? Now, y2 is going to be y1 plus h times f of x of 1, y of 1. And that's going to give me 1.5 plus 0.5 times 1.5. And plugging all that in, so 0.5 of 1.5 is 0.75. Adding that to 1.5 gets me to 2.25. Right, and so that gets me roughly here. Okay, so now let's take a look and see what happens with 4 steps. And this is really where I'm going to stop because I only have so much patience. Right, so here our h is going to be 0.25. And so let's go ahead and copy that over here. So step size is 1/4. So h is equal to 0.25. Right? Right. So now let's do this in, say, green. So again, we have a new y1. So it's going to be y of 0 plus h times f of x of 0, y of 0. And this is going to give me 1 plus 0.25 times 1. Right? So this gets me 1.25. And so let's choose a square. And so this is what I get. I get a square. Okay, now let's figure out y2. y2 is equal to y1 plus h times f of x1, y1. And so it's going to give me 1.25 plus 0.25 times 1.25. And forgive me, this is the point where I'm going to pull out a calculator. Right? So let's see. So we got 1.25 divided by 4. And then we're going to add 1.25 back to that. And that's going to give me 1.5625. So about 1.5. So yeah, it's actually pretty close to what we had here. Okay, so we have agreement there. Now let's do the next one. So we have y3 is equal to y2 plus h times f of x2, y2. And so this is 1.5625 plus 0.25 times 1.565, and excuse me, while I put this in the calculator, so we take 1.565 divided by 4, and that's going to be added to 1.565. Crap. Not 65. Okay. 25. There we go. All right. So now we have 1.5625 times. Actually, it's going to be 1.25 is everything put together, right? So we get this is equal to 1.953125. Okay, and so it's just shy of 2. So it's going to be here. Okay, now last one. So we get y of 4 is equal to y3 plus h times f of x3, y3. And what does this give me? It is 1.953 plus 0.25 times 1.93 125. And so let's go ahead and figure that out. So this is going to be times 1.25. What does that give me? It gives me 2.44. So, so here is yet again closer. Okay, cool. Okay, so something we can exploit is that this y and this y are the same, so we can actually factor them out. So in general, actually, if you take a look at this, we have that yn plus 1 is equal to y of n plus h times y of n. So this is really 1 plus h times yn. And so you can actually work pretty fast for this particular differential equation. So for this particular IVP, we have this, right? Do not confuse it for the general equation, but just for here, because we have such a simple y, we get that. So if you actually have a calculator, it becomes pretty trivial in order to do this for more. So let me just go ahead and do this 8 steps all at once on my calculator. So I'm basically going to put in 1 is my base, and so that is my initial value. And now I'm going to multiply it by, now we want 8, let's try 8 steps. And let's see what we get. So we get, so let's see, 1, 2, 3, 4, 5, 6, 7, 8. And so if I do 8 steps, I get even closer. And so let's do this in orange, and I get, actually I think I overdid it by 1. So divided by 1. Get 2.56. So here, yeah, let's say this be 8 steps, and here we're at 2.565, blah blah blah, which is closer than the last one. And oh, I didn't even write that last one. What was the last one again? So 1.953.125, and then multiply that by 1.25 gave me 2.44 in green. So I said it, but I didn't write it down. So this was 2.44. Okay, so so then the idea is that each time I add more steps, it looks like I'm actually increasing to what we're aiming for, which is about 2.7. We don't quite get there yet, and it'll take a lot of approximations in order to actually get to that point. But it's honestly not that bad. And what we know is that if we decrease the step size, so we went from just one step gave us this, which was fairly far off. But when we made it so we took 4 steps, we're able to do that a lot. We can get a lot closer. Like we increase by like 0.5 there. So that's nice. And so basically we have a way of sort of quantifying how we can get closer, and we know if we make h really small, we should get closer to the value. Now, there's other caveats that come into play, like computationally, if we make h really small, we actually start getting bad numbers because we're going to have a lot of round-off errors that'll accumulate. But in principle, small h's should lead to good solutions. Okay, so let's go ahead and take a look at this in MATLAB. And so we'll just switch to MATLAB at midnight.
All right. I guess welcome back to MATLAB at midnight. I don't know. It is rough doing this on days I watch my children. Wake up at like 5:30 in the morning and push through until like really late, and then still have to get some work done. They're quiet, so it's time to record. In any case, yeah, so we're going to go over, talk about some direction fields, and I interface some of the Euler method in this case. So I did something kind of fancy, and maybe it's a little too fancy, and so I might dumb it down in a minute, and so show you the more basic way of doing this. But I think this first way is going to be kind of instructive in showing you how direction fields influence the trajectory. Okay, so why don't we go ahead and get started. Let's see. So let's take a look at the direction fields. Okay, so here I have two equations. So I'm toggling between them like I did before with this variable here. And so the first equation is going to be t minus y squared. I think this was one of the examples we talked about. And I set the t to be equal to 3. And so I just sort of set, wherever we start, we're going to run for 3 seconds, or whatever you want to call that. And then the second one is going to be the circle equation. So minus x over y, or in this case, minus t over y. All right. So first thing we're going to do is make a direction field. And so in MATLAB, you need something called a mesh grid. And so this is going to collect all the x values, and it's going to repeat the x values here. So if I go and copy that and paste it here, you'll see. So if I say x, so each row gets repeated with the same x, or each column gets repeated with the same x, and then if I type in y, you'll see, it's harder to see here actually, there we go. So each row gets repeated with the same y. And so when you put these two together, you want to look at the ijth coordinate, then you're going to put xij comma yij, and that gives you the actual vector that you want, or the x and y points. So now a direction field basically needs two things. So MATLAB doesn't actually have a pure direction field option. It has a vector field. And so one of these vector fields, I'm just going to make everything with just ones. So it just always going in the same direction. And then the v is the one that's actually going to be changing everything. And but if I was doing something out of, say, calculus 3, and I need like a potential field or something like that, or sorry, a vector field, then I would adjust the u coordinate would have its own variable. But here it's just one; it's always going forward. So u represents the x direction, or the t direction in this case, and v represents the y direction. Okay, so this one, it says zeros, but I basically need to fill it up, so this is just a placeholder. So then I have this double for loop that's basically going to run through all the i's and all the j's, and it goes through all the different coordinates. You can see this is where I have my xy point. And so I feed them into F, which is my dynamics, or my differential equation, sorry, habit from control theory. And so you put that in there, and then it just records it into V, and then it moves on to the next one. Okay. Now at the end of the day, we want to normalize all these directions, and so this is a normalization. So make sure that everything shows a unit vector. Okay. This is quiver function is what actually makes those, and it makes the direction field, and then this would give me the direction field, just this top half. The bottom half is actually Euler's method, and so I grabbed this off of the MATLAB MathWorks help website, and somebody gave so basically I can take a few coordinates off of a figure, and I can record the points that those are. And so just to be fancy, I am using this to collect my, I'm collecting 4 total points of initial points. So we can see 4 different trajectories once I play this. And so then it basically goes to Euler's method. So we have a time step of 0.001. And using that time step, I'm just writing out what all the t values or the xi's are going to be. Now, again, I initialize y being zeros. This is again going to be another initialization of my time. So this is one time point, kind of. I just kind of wanted to get the length of this. That's all I'm really using it for. But then in this case, I'm actually going to I am actually going to put all the actual t values in here. Since we have different initial starting points, they're going to be shifted from each other, so I have to be careful about that. So I go ahead and generate the time points. It's pretty simple. This is MATLAB's make a vector of just consecutive time points, and then I record all my initial points here. So what makes this more difficult is that I have to I actually have to record these t's and these y's separately, just because we're going to actually have a whole matrix of these. I'll upload a much simpler version of Euler's method, where you just give it one time point, and then and one initial point it'll run through. But since I'm running it several initial points, and I am basically doing all this in a loop. So in any case, so let's go ahead and take a look. So this is basically running Euler's method. You can see here it takes takes the initial point, and then it goes to the next point here by looking at the previous point. And so in the first one, this would be just the initial point, plus h times the differential equation evaluated at the previous point. So this is the initial y, and this would be the initial t in the first step. And then in the next step, it would go to the next consecutive one and just use the last previous one. So, yeah. So this here is just Euler's method. But I'll have a separate Euler's method code for you guys to take a look at later. Alright, so let's go ahead and run it. So let's see what we get. Okay, so it looks like I had equation 1 toggled. So this is the t minus y squared. And what's interesting is you'll see that we have a bunch of these arrows that are kind of going like this, and then they go back up like this. But then there's this whole chunk here that is sort of like a straight line, and then just below it everything's descending. I'll show you in a second, but if I pick anything below here, they're just going to blow up, and this is sort of the finite escape time that engineers worry about. But if I stay on this side, you can actually get some pretty interesting looking curves. So I just have to be careful about that one line. And I guess I'll pick something here too. All right, and oops, right click, not left click. Let's see. And boom. There we go. All right, so those are my initial points. So you see, we can see here that the curve more or less follows exactly what we see with these arrows. It might not be exact. Keep in mind, the Euler's method is approximate, so it might not be perfect all the time. It looks like something's kind of going wrong here, but not too bad. And so yeah, so basically it follows the curve pretty well. And it seems like we sort of have this sort of asymptotic trajectory, right? So in the long run, everybody seems to converge here. And so if you start up here, it looks like you're eventually going to crash into whatever this curve is that it runs into. So that's interesting. All right, now we can do some more exploration. Let's run it again. So I can say, so we saw when I picked some things up here, so like here, here, or here, everything worked out fine. But then once I pick, watch what happens when I pick here. So I pick this guy, and boop! I mean, 10 to the, I mean, what is that? That's a 10 to the 157th. That's a big blow up. And it just sort of flattened everything else out here. And so, and MATLAB more or less just gave up. So yeah, so this is something like, if you think of like with tangent, right? If you put in anything close to what should be an asymptotic blow up for tangent, that's what will end up happening. So that's happening here to us. But yeah, so it looks like it was probably finite for a while and then poof, dead. So yeah. Okay, cool. Now let's take a look at another one. And this shows a different sort of problem that comes up numerically. So let's take a look at equation 2. So with equation 2, what do we get? So this is a circle, right? You can see basically all these lines going this way. But look what happens when I start over here. It's not like anything, it's not like with a circle, it goes here and then it goes back around this way. We're always going to the right with our x values, or our t values. So it goes up, 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 down, 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 boom, and then it faces these arrows that are saying you should go the other way. If you started down here, then these go down, down, up, and then up, 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 up. And so that's what this direction field is doing. And now, so let's see if I can pick a couple of points. 3 and say 4. Let's see what they do. So yeah, so these trajectories go more or less circular, right? They go up and this way, and yeah, so it's a circle, right? Pretty easy. Now what's interesting though is what happens when they hit here, because technically we're not going to have a function anymore if it actually crosses and goes the other way, and so we actually just have to stop the entire simulation right when it hits this point. And if we don't, we get some weird blowups, because these are basically, when you hit the x-axis, y is going to, remember, is t divided by y, minus t divided by y. And so when you divide by y, that's going to give you something nearly infinite when you're at near y equals 0. So so let's take a look. So let's see. So I'll put something nice here, and I'll put something nice here. Yeah, I'll put something nice here, but then let me just throw a curveball. Boom. There we go. So we see a bunch of different phenomena happening here. And so that's just what happens numerically when you try to do this. So in reality, the curve stopped there. I mean, there's just no going beyond that. That's the end of the function. But since this is numerical, it actually kind of jumped past this point, the y equals 0 line, the x-axis. So it went just past it, and then it got told, man, this should be a nearly infinite jump in the other direction. What are you doing here? And so it jumps up, and it's like, okay, well now I'm good again, and then it jumps up again, and it's like, oh no. And then we saw this one, it had the same sort of jittering here, and then what ended up happening is it came around here, and it made it quite a bit down, and then it said, oh, I didn't know I was supposed to go this way, so I'll go this way, blah, 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 blah. And then it hits this point, and it just gets thrown up. If I actually change the step size, it gets a lot worse. But yeah, so yeah, so I thought that was interesting. But in general, for the true bits of the curve, I mean, it's good to see that we have a sort of agreement between these direction field markers and slope fields and the actual numerical trajectory. So that's where it gives you sort of confidence in these methods. And of course, we know that the solution to this is actually a circle. So we see circle-y things. The scale is not quite perfect, but that's fine. This is just we're not publishing this in the paper. We're just putting it on YouTube for the entire world to see. So I mean, who cares? Okay, cool. Yeah. So I have some other things in the works. So next thing we have is the separation of variables, or separable differential equations. And for that one, we end up getting a lot of implicit solutions. And so that gives me an opportunity to give you a throwback to what's called Newton's method, which you learned back in Calculus 1, depending on your Calculus 1 class. I don't know what they teach in there nowadays. And so you get to see how we can actually actually solve those equations that we get at the end of the day. So that's fun. But yeah, I think I need to go to bed. In any case, have a good night, and I guess we'll cut to the outro. Okay, welcome back. So that was slope fields and Euler's method. So Euler's method, super simple. It's like 2 lines, and you just keep executing it over and over again. When it comes to an exam, I'm going to expect you to, say, do it by hand, but I mean, I certainly won't give you anything that's more difficult than, say, multiplying 0.1 to itself or something like that. So I mean, don't worry, you're not doing any sort of sophisticated like square rooting or anything else like that on the exam. We just don't have time for that. But yeah, so it's yeah, and slope fields, they're pretty straightforward. What you really need to do is, if you want to get those right, is you should just go back to your pre-calculus textbook or whatever and review things like conic sections like parabolas, ellipses, hyperbolas, because I mean, those are really the only things I can ask you to reasonably graph, other than, say, a parabola of some kind. And so go back and polynomial of some kind. Parabola is a conic section. In any case, so yeah, so go back and review those, make sure you get those right, and then you should be fine as far as any question that comes up with isolines or anything else like that on the exam. In any case, yeah, so I hope you learned something, and I'll see you next time.